Good morning, good afternoon, or good evening, depending on when you're going to be watching this. My name is Silvano Coriani. I'm a program manager in the Azure SQL team, and I'm here welcoming you to this session about how to leverage Azure SQL database for running hybrid transactional and analytical processing workloads, or HTAP. So the agenda for today is we'll start with a kind of brief introduction on what is effectively HTAP and how it is different from other type of workloads, more traditional workloads like OLTP or OLAP/data warehousing. Then we will see what kind of specific features and capabilities Azure SQL is offering to deal with hybrid workloads. And we will introduce the concept of real-time operational analytics and see how, again, you can build solutions with Azure SQL to solve some of those problems and scenarios. And then we will go through some of the enhancements you may have for running analytical workloads, and specifically we will look at window functions as one of the powerful tools that we have in our kit to effectively run the analytical portion of some of the workloads in Azure SQL. Let's start from defining, again, what are the traditional database workloads that we are running on our systems. OLTP, or online transactional processing, is probably one of the original database workloads that everybody is getting in contact with. And we know OLTP solutions typically are kind of adopting highly normalized data models that are really optimized, designed for concurrent data operations, data modifications, and read operations, right, where we have very selective queries, in most cases kind of point lookup queries that are supported by proper kind of indexes. And they are optimized for fast retrievals and for, again, concurrent data modifications. The relational engine itself is providing is enforcing consistency through the usage of constraints, domain constraints, referential integrity constraints, and so on. On the other hand, the traditional kind of analytical processing workloads are usually designed around denormalized data models, where a lot of data is actually replicated or duplicated across tables within that data model. And those are optimized for typically for kind of heavy read and low write type of workloads. Right? A lot of aggregations and large kind of scans of data on those tables, and except for kind of data loading, so when basically we are feeding data into our data stores, the workload is mainly read only, right? And again, we may have large scans or ranges of data that we are accessing and running aggregations on top of that. So in the ideal world, those are the two kind of ends of the spectrum of the kind of workloads that we can run against a database. In reality, what we see customers running are mixed workloads, right? Where we have a combination of OLTP and OLAP type of queries that are hitting our data stores. And where we may have transactional operations against our database, while at the same time we are also performing some some large kind of analytical queries that are maybe aggregating data or doing some kind of analysis. Right? In real life, effectively, most of the database workloads actually belong to this category, right? Because nothing is really pure OLTP or pure OLAP, except for kind of some very few kind of cases, right? Gartner, the kind of analyst company, coined a specific term for describing these hybrid transactional workloads and transactional analytical workloads, and they call it HTAP. HTAP is basically this kind of merge between the OLAP and the OLTP workloads, and based on Gartner's definition, it is enabled by in-memory technologies, right? Because through in-memory technologies we can power OLTP solutions, and we can make sure that we have the highest kind of transactional results in terms of performance, in terms of concurrency, but at the same time, we can execute this analytical portion of our workloads on top of the same transactional data, right? So SQL Server, starting from 2016, has been receiving a lot of good kind of reviews, as you can see here, and is effectively one of the key technologies in that kind of landscape to enable the creation of HTAP-based solutions. So what kind of technologies and capabilities are needed in order to enable HTAP solutions? So effectively, by creating columnar indexes on top of OLTP tables, either in memory or disk-based, we can provide the ability to run those large scans and aggregations while the underlying kind of OLTP portion of our workload is still running, right? And by kind of enabling or enhancing the existing OLTP T-SQL surface area, we can effectively add new capabilities from a language perspective to enable these analytical workloads on top of OLTP data. At the same time, by scaling to higher kind of compute and memory resources, we can effectively again run those mixed workloads against the same kind of engines without competing for the same set of resources, right? So the benefits from this approach are that in some cases you can effectively eliminate the need for having ETL processes that are feeding an external engine like a data warehouse system just for these kind of real-time operational analytics scenarios, right? So if you have an existing centralized enterprise data warehouse, you probably still continue to use that, but again, for those real-time analytical scenarios, you can effectively eliminate the need for having this centralized data warehouse system. At the same time, you can get a lot of kind of performance improvements, both from a transactional standpoint by enabling this in-memory capabilities, and also from analytical query perspective, you can get a boost from having these column store structures in place to again run aggregations in a very effective way. So let's take, for example, as an example, a classic credit card transactions processing system. We can again combine the abilities of the in-memory OLTP capabilities of the SQL Server engine and the in-memory column store capabilities to run HTAP workloads, like, for example, real-time fraud detection. Right? So we don't need to wait for the entire ETL process to happen before being able to run analytical queries on top of the same kind of data structures. So what are the kind of trends that are basically making HTAP workloads happen? We start typically from the fact that our systems are getting more and more memory effectively available, NVRAM and other kind of memory enhancements are getting more accessible from a price perspective, right? So we have systems that have a lot more memory available, right? At the same time, we have a lot more cores in our processors, and it's this trend is basically contrasting the fact that our CPU clock rates are not going to increase a lot from a kind of physics perspective, but we have a lot more cores, right? So we can improve kind of concurrency and provide kind of lock-free type of algorithms that are again boosting concurrency, right? At the same time, from an architectural pillars perspective, by moving a lot of our workloads to in-memory and having the kind of data engines are getting more and more optimized, the entire stack can get a lot more kind of performance around data operations as they are effectively happening in memory. At the same time, by compiling our data access code, our T-SQL code to native machine code, we can again make data access code faster and effectively power our business logic functions and procedures in order to use our kind of compute resources more effectively, right? The good thing is we are basically enabling these new capabilities by maintaining a fully integrated experience with the existing components of the relational engine, right? So we can manage our kind of memory optimized structures, tables and procedures and such by using exactly the same tools, same approach, and effectively just kind of benefiting from those new capabilities while we don't need to reinvent the wheel or to relearn new features and capabilities. From an Azure SQL perspective, those in-memory capabilities are usually available in the highest kind of service tiers, specifically premium and business critical, provide in-memory optimized tables, for example. Hyperscale service tier only supports for now memory optimized table variables, and we can effectively compile the modules and store procedures in native code, but we don't have yet the in-memory OLTP tables in hyperscale. It's important to understand for Azure SQL that we have a proportional sizing from basically the amount of memory available for in-memory OLTP tables that depends on effectively the compute size of your Azure SQL database. Okay, so if you start small from a compute size perspective, you will have a portion of the system memory available for in-memory OLTP tables. Then you can scale up to basically largest compute sizes if you effectively need more in-memory data space. So we can make our kind of analytical workload faster. Effectively, column store index has been a great enhancement. Both clustered and non-clustered column stores are helping analytical workloads because, usually we have data stored as rows in our traditional row-based tables. The data stored as rows, as individual rows, is ideal for OLTP type of workloads, where we need to access effectively a small set of rows. We need to do point lookup operations, modifying data in one specific one or more columns of a small set of rows. These row-based tables are still very, very effective. But at the same time, with column store indexes, we can effectively store data as columns, right? So the same table, we can basically divide it into row groups, so groups of rows, effectively, and for each of the columns that we have in our table, we can effectively create a compressed segment which is containing all the values for all the rows in that particular row group, and this is basically helping in improving compression, because data that belongs to the same domain, so the same data type, and in most cases a lot of data can be effectively duplicated, are compressing better. And we can help reducing I/O operations needed, because we can only retrieve those columns and those row groups that are effectively needed for solving a particular query, right? And with this particular structure, we can fit more data in memory, and we can optimize the way the CPU is effectively processing those vectors of values that are basically loaded as part of the query processing through this new processing mode called batch. Batch mode is effectively a way to kind of optimize how the relational engine is using the CPU underneath, and batch mode processing is basically has been introduced on column store indexes only. Now with the SQL Server 2019 and Azure SQL with compatibility level 150 for our databases, can effectively provide the same batch mode also for row stores. But still, from a data organization perspective, with column store, it's very likely that we are going to benefit from batch mode in terms of performance on how we execute our analytical queries. It's important to understand that for Azure SQL, we are making column store indexes available on all service tiers and compute sizes, except for kind of basic and the smallest kind of standard compute sizes like S0, S1, and S2. That's because the amount of memory and compute power for those very small instances is not enough for dealing with significant kind of column store index based tables, right? So you need to start at least from S3, which is again a single core type of instance in order to be able to use column store. So if we have a typical analytical architecture where we have two separate systems here, one is accepting transactions where users are executing operations against the database. We need effectively a second system, like for example Azure Synapse Analytics. We need to do the data movement, ETL, and loading into the analytical system in order to be able to run our reporting or dashboarding type of workloads, right? This solution is great if, for example, we have maybe a lot of transactional systems, and we want to aggregate all of them into a single analytical solution. But it's a complex way of implementing solutions if we only need, again, to run some sort of real-time analytics on top of these transactional data, right? This system is also intrinsically introducing latency, because you cannot run kind of a continuous ETL process here. You typically have to do it in batches, and this means that you can only do that with a given kind of time interval between the two systems. What to do in order to minimize this kind of latency is effectively what we've been discussing here, right? So adding a column store index dedicated to the analytical portion of our workload is effectively enabling what we call real-time analytics, right? So in this way, we can eliminate ETL, we can eliminate kind of this data latency. We don't need necessarily a separate data warehouse system anymore. Yes, maybe, again, our centralized data warehousing system is still needed if we have multiple systems that we want to consolidate. But again, for a lot of customers, this is not necessarily needed, right? We still have a challenge here, which is, hey, how can I make sure that I'm minimizing the impact on my transactional system, because that's where kind of my money is coming from. So I want to make sure that I'm not slowing down the ability to run transactions while I can still run this analytical queries. So SQL Server and Azure SQL are providing some specific capabilities in order to minimize this impact. So first of all, we can create what is called non-clustered column store index on top of our OLTP data. So we have our kind of B3 index here and our relational tables that are accepting transactions and such. We can create a NCCI, so a non-clustered column store index, making sure that effectively only let's say the more steady and stable portion of our tables will get compressed and transformed into this column-based structure, while again all the new operations, new insertions and so on are effectively happening in what is called delta row groups. So those delta row groups are still kind of row-based portions of our table, where we can effectively accommodate all the new changes. So this means insertions and in also deletions or updates are effectively happening here, and we keep this portion of the column store based segments intact. And the query optimizer effectively will choose if to support a particular query, he needs to access the column store index or the other existing relational and B3 indexes that are created here. Right. So let's take a look at a quick demo that is showing how we can make it effective. So what we have here is the wide world importers sample database that you can download from the official samples in SQL Server, and we are effectively running a set of queries here against the order lines table. Okay, in this moment I have a synthetic workload which is effectively hitting my test database here. I have 50 parallel threads that are inserting thousands of rows per second, right? This is the average insertion time, see 134 milliseconds. And we can take a look, right now, I think this table has around 1.3 billion records, right? So it's a quite kind of large database. You can see, this is my Azure portal showing around 775 gigabyte of used space in my database, all right? Okay, and just to show you that effectively that workload is running, I'm running a quick calculation here to show you that right now, yeah, there are around 3,000 rows per second that are getting inserted into this particular table. Okay, so it's a pretty interesting one. Let's see how effectively we can leverage non-clustered column store indexes for running HTAP, right? So we created a non-clustered column store index here. We can look at these DMVs, this particular DMV, which is column store row group physical stats, to see how our non-clustered column store index on top of the order lines table is effectively organized. Here we see these are all the row groups, so we have around 1,200 row groups for now, and one important aspect to highlight here is you see most of, if not all of the row groups are effectively compressed. This means that the structure of the column store index has been created. You see that for most of them, the amount of rows in that particular row group is around 1 million. So this is effectively a system managed value, which means that these particular row groups are very well compressed and effective, right? And there is an open one, which is the one where we are effectively accumulating all the new rows that are getting inserted right now in the system, right? So here you can see, instead of having all the traditional kind of data pages for our table, large table here, we are organizing with this non-clustered column store in order to be able to keep running our fast kind of order insertion tool here while we are effectively also executing some analytical queries. So I want to show you the difference of using the non-clustered column store when we are running some form of analytical queries here versus the underlying kind of row store. Right? So I have an analytical query here, which is basically calculating the sum of the quantity minus the picked quantity, so effectively the allocated quantity for all the stock items that we have in our warehouse, right? And if we run this particular query here by providing we have a query hint here that says ignore non-clustered column store index, and we can and then we are basically recording how much time is taking this query here, right? So I'm executing this and this is going to take a long time, okay? And because again, the query is very, is basically aggregating and scanning the entire table. And because we don't have, we are forcing the query engine to not consider the non-clustered column store index that we have, this is probably going to run for minutes, right? And we can see the difference. We can cancel this for now and see what's going on when instead we are running the exact same query, right? But without that hint.
So we can see that, again, the query scanning 1.3 billion rows and more than 700 gigabytes is effectively running in around 5 seconds, right? Which is I would say a good result for, again, let's say running a report or a kind of a quick analytical query on top of our very large table here, right? And the reason why we have this very fast approach is, again, I'm just showing you the query plan, the estimated query plan here, and we can see now we are using effectively the column store index and the estimated execution mode here is batch, right? So the combination of optimized kind of underlying data structure and the batch execution mode is effectively powering the query plan for this particular analytical query, which is, again, remember, is running while we are inserting thousands of rows per second on the same table. So over the last few releases of SQL Server, of the SQL Server engine, we've been adding some new capabilities and tuned how column store indexes are working to minimize effectively the overhead of the clustered column store on top of these OLTP workloads that are running on the same table, right? So we know that there is some overhead because in a typical kind of B3 in a typical B3 based table, when we insert is typically kind of quite fast. When we are deleting a row, we just kind of seek the rows to be deleted, and then we effectively delete the row. Same for the update. But we know that when we create a column store index, we have to maintain those external structures, like, for example, the delta stores, in order to kind of be able to accept changes to our column store structures, right? So, and some of these operations are effectively taking a bit longer. Like, for example, when we are deleting a row, which is we need to first of all understand if that row is still in the delta store, so it's still in a kind of row-based format, or and by the way, there can be multiple versions of that particular row in the data store, or the data has been already compressed and part of a segment, and in that case, what we do is basically we create a row buffer with all the keys of rows that needs to be deleted, right? So in order to minimize these operations that, again, can be a bit more kind of heavy for the engine, we've been improving in some areas the engine. Like, for example, to make sure that inserting rows into the delta store is faster, we kind of removed the page level compression that we originally had for the row store, making sure that this way inserting is faster. At the same time, we are effectively potentially increasing exponentially the size of the delta store, delta row groups, kind of to make sure that if we can the hot portion of the data in that table can stay in the row store mode longer than and before it gets compressed as part of the remaining portion of the index. And for reclaiming deleted rows, we can typically customers can run alter index reorganized in order to make sure that basically those changes for deleted rows are merged into the main column store segments, or effectively there's a new background thread that we will talk about later on that is doing this for us. So alter index is not necessarily needed anymore. So few other improvements. Remember we have our B3 index structure, our kind of OLTP table here, and when we insert new data, we typically have the kind of hot portion of the table where the new records are going to be introduced. And if in our workload there are records that stays hot, for example, for a long time, for some time, like for example, when I'm inserting a new order in my system, I know that I have over a certain time period that record can be modified, because again there may be a procedure in place where customers can update it, or there may be some other automatic processes that keeps modifying that record for a given amount of time, right? So in order to deal with this situation, there is an option when we create a non-clustered column store index to specify what we call compression delay. This means that for this particular amount of time, new data that are living in the row store here in the delta store will stay there for that amount of time, and only after that amount of time will basically get compressed and be part of the non-clustered column store structure, right? So again, this can help in those situations where data stays hot for a given amount of time that we can kind of predict, right? And until that delay, data will belong to the delta store here. After that, data can get compressed and be part of the column store. At the same time, another way to control, if you will, the amount of time is to create the amount of time that a row is hot is basically to create a non-clustered column store which is filtered, right? Like for example, we can create if let's say we know that until, for example, a particular sales order is not shipped, it may be modified, right? So for example, by creating the column store index where order status equals shipped means that only when data is shipped it can effectively be compressed and be part of the column store structure, right? Until that, data will basically stay hot. And what is interesting here is that the engine behind the scenes will effectively look at the portion of the data which is hot, so where basically the clustered index, the non-column store index here is used and can, for example, concatenate and merge data for solving this particular query with the data that are stored in the column store section of our table, right? So this means that you don't have to do anything, and if you have, like for example, a query, select top 5, some group by and so on, the engine itself will take care of merging again the filtered and the non-filtered data and basically return whatever is needed in a very efficient way, right? This is a very powerful concept. And again, as an extreme, in order to minimize the potential overhead of a column store on top of OLTP data, what we can do is we can create replicas, right? Readable replicas, and those replicas can effectively scale out the way we are running the analytical portion of the workload on top of the same data. So we are effectively detaching the kind of OLTP system from the analytical queries, and the only latency from the the newly inserted data into the OLTP portion of the database will be basically the one related to the geo-replication here, which is typically very fast and is effectively replicated in few seconds, right? If you had to do the same with a typical ETL process, this will probably go into the at least minutes, right? Type of latency. So this is an acceptable approach in terms of kind of minimizing the overhead on very kind of highly impacted kind of OLTP systems while we are running those analytical queries on top of the data. Okay, so we have been talking about column store, right? And we at the same time we talked about having a kind of in-memory optimized tables for kind of helping a highly concurrent and transactional system. But why not combining these two technologies, right? So let's say we have this kind of in-memory OLTP table where we have the kind of traditional OLTP type of indexes on top of, right? What is interesting is the ability to effectively create a column store index on top of in-memory OLTP tables and effectively execute all the OLTP operations, keep using kind of all the OLTP operations, including inserting, kind of deleting, modifying data, and again benefiting from both in-memory technologies here, column store and OLTP optimized tables, to again run some analytical queries on top of the data in the in-memory format here, right? We still have, as we've been discussing, the ability to do the compression delay option for hot data, right? So the hot portion of our in-memory OLTP table can stay in the delta row group format, while the more kind of old historical data belonging to the same in-memory OLTP table will be added to our kind of segments and row groups here. We can do this for data that are fully kind of resident in memory, and we can persist data and metadata so that data will be available, kind of will be durable over time, right? And you don't need to change effectively your LTP application in order to be able to benefiting from both technologies. This is a very, very interesting and powerful tool that we have. Okay, let's run a quick demo here, which is showing us the benefits of running in-memory OLTP optimized tables for kind of concurrent workloads. We have a simple kind of workload here, which is inserting like 50,000 records in a table, which is tracking the location for our kind of vehicles fleet. And what we are doing here, very simple, we are looping 50,000 times against and we are invoking a stored procedure here, which is basically inserting records into a on-disk table. This is not an in-memory optimized one, and we can run this and see after a few seconds how long it takes. Again, here we are just invoking a number of times, and you see, this is around 12 seconds, right? The amount of time needed. Now we have a storage procedure here, which is, let me show you, which is basically doing that insert operation. This time is doing against an in-memory table, and what is even more important, we are basically compiling this storage procedure natively. So this is going to be translated into effectively a native code procedure in our system. And if we do execute the exact same logic here, so we are looping 50,000 times, but this time inserting into our in-memory table through native compiled story procedure here, we see that we go from 12 seconds down to 3.6 seconds, okay? So we are still, notice we are still looping 50,000 times here. The only portion of our natively compiled code is within that story procedure, which is doing a simple insert, right? But still, you know, this is taking like 1/3 of the original time. Now, let's do something kind of different here, right? So we created another story procedure here, which is basically compiling the entire loop, right? So instead of having a T-SQL loop, which is interpreted and invoking a natively compiled story procedure, we are compiling the entire loop here, and then we are invoking the singleton story procedure directly within this this parent story procedure. And again, we can see that inserting the same 50,000 records now is effectively taking less than 1 second. Okay, actually quite less. So it's basically 10 times faster than the previous example that we created, right? So we can see this way how we can effectively power and boost the performance of kind of highly optimal, you know, high insertion workloads. Okay, let's continue the demo here and see if we can combine column store and InMemoryLTP tables together. So the table we are inserting here is, again, a bit more than 10 million rows, not that much, but anyway, when we are doing executing a point-to-cap query, we are effectively very, very fast. We are talking about kind of 5 single-digit milliseconds. And if we take a look at the estimated query plan, we are accessing, you know, the primary key supporting index here, and of course the estimated cost is very, very low. If we are instead executing more type of analytical query, we are scanning the entire table here and calculating the average. It is still fast. It's in the hundreds of milliseconds, but if we take a look at the query plan here, we see that effectively we are scanning the entire table, and the estimated execution mode here is raw. Okay, so this is something we can probably improve, and what we need to do here is to effectively create a clustered column store on top of the same InMemoryLTP table, right? So let's run this. And let's see now how this query runs. It's again quite fast. And if we look at the query plan now, this of course has changed. Now we have a batch estimated execution mode. We are effectively scanning the column store index that we just created. And if we look at the cost has moved from 19 down to 2.5. Okay, so this is what the kind of combination of InMemoryLTP optimized tables and clustered column stores on top of in-memory data to be able to run both analytical and transactional workloads on the same underlying structure. As I mentioned, over the course of the last few releases of SQL Server, those technologies have been highly improved. And in Azure SQL, we have the ability to set compatibility mode at the database level in order to be able to get these improvements available for our Azure SQL databases. So with 150 compatibility mode now, we have batch mode on row store available, so the ability to run some kind of analytical workloads effectively even without requiring column store indexes, so that the batch the batch execution mode can power those queries, those analytical queries, while we cannot effectively build a column store, right? Where the column store is adding too much overhead, for example, we have a very high kind of transactional workload. This is definitely a good option, and it's again, it's a good compromise for running analytical queries on kind of OLTP tables. At the same time, we've been adding a lot of online and resumable operations for building the column store and rebuild the column store. So workloads will not be blocked, data changes that we made to the underlying data are basically added transparently to the target column store table. There's a new there are two new options to the SP estimate data compression savings. Column store and column store archive now basically let us estimate what kind of space saving we can have when we create a column store index on a table by using both kind of standard and archive type of compression, while archive is a bit more kind of CPU heavy, and while building it can save a lot of space in our databases. And the kind of online row store index rebuild is now a resumable operation, so we can resume a stopped operation previously. As I mentioned, another improvement that has been added, the background merge task. So tuple mover, which is the mechanism creating, compressing, and sealing kind of row groups, is now kind of automatically stop. Okay, so for background merge task is another improvement that we've been adding, which is basically helping the tuple mover in merging those delta row groups, smaller open delta row groups into row groups when a large number of rows have been deleted. Right, so this mechanism previously was requiring an index reorg operation. Now, this is not necessarily needed anymore, and basically this background merge task is effectively improving the quality of the column store index organization over time. Right, so very important for the kind of health state of our column store indexes. Okay, so when we talk about operational analytics, so running again analytical queries on top of operational data stores, what kind of analytical queries we are effectively running, right? Yes, of course, aggregations, sums, and so on. But when we are dealing with transactional entities like kind of sales orders, inventories, warehouses, replenishments, and so on, it's very helpful to execute analytical queries that are returning a mix of detailed and aggregated data, right? Think about problems like kind of calculating running totals, and
moving averages, comparing week over week, so time periods, and so on. So those are typical business problems that can be solved in a very efficient way by leveraging what are called window functions, right? If you want to know everything about window function, I definitely recommend you to take a look at this book from my friend Itzik Bengan, and it's the go-to place to learn everything about window functions. But I'm gonna give you a kind of a quick overview about this powerful tool over the next few minutes, right? So again, we have let's say we have a list of line order items here. So we are selling for a given kind of stock item in our catalog. We are selling some quantities, right? Those are kind of order IDs, and we are selling some quantities, and we want to calculate the kind of running total, the amount of total that we are selling over a given time period here, right? And with all these different order IDs. So you can see that this table here, this result set here, is combining detailed data. So these are effectively the order lines that we are selling, but also aggregated data, like again the running total, or what is the percentage over the total amount of items that we are selling of this particular item ID in this time window, right? So these are effectively examples of what we want to calculate, for example, per order. We would like to see, for example, I don't know, the sum of the kind of rolling 4 weeks by product, the percent of contribution for a single record to another, or to the grand total, and so on. So those are typical problems that we need to face with this kind of mixed analytical workloads. And the way we were solving this traditionally was typically through, let's say, correlated subqueries, like, in this case, for example, what I'm doing, I'm, of course, returning the detailed kind of columns here, but at the same time, I'm also executing some correlated subqueries to calculate, for example, the running total, summing all the kind of order IDs until the current one, right, for a given item ID, and same for example, calculating the percentage of a given line on the total. This is not a super complex query. And what is the problem? The problem is that depending on the size of the filters that we are making, that we are specifying here, like for example the time window, this is running for the last 15 minutes, for example, and for a given stock item, the performance of this query can get kind of exponentially bad, right? Because the amount of calculations here are basically going to explode. And you can see this is a kind of a query plan of that previous query, where, for example, this is going to take hundreds of seconds or even more to execute. Yeah, we can try to optimize this, but the problem, this kind of n-squared problem, is there. So this is where we can effectively leverage window functions, right? And this is an example of where we are effectively specifying the same columns here, but this is the syntax that we use to effectively enable window functions. So we are summing the quantity over is the keyword here, and a partition of stock item IDs. So we are partitioning over the ID that we are interested in,
and we are ordering that window function on order ID, and we are summing basically on all the rows that are preceding the current one. Okay, so through this syntax, the engine, the database engine, is effectively doing that same operations that we were doing with those correlated subqueries, right? And then we have, you know, whatever predicate here to kind of frame, to define what is the size of the window of the result set we are operating on top of here. As you will see in a live demo, performance here are super good, and we can effectively, again, while the same database is processing OLTP operations on top of that, we are processing that you know, portion of the table of the you know, 1.3 billion rows table in a fraction of a second, right? And this is because, again, the batch execution mode, in addition to these new operators, you know, query plan operators that are taking care of the aggregations for the Windows functions, are very, very powerful, and are providing, you know, the magic behind the scenes. Okay, so let's see it in action. This is the same query that we had on the slide previously, right? So what I'm doing here, I'm basically just selecting, you know, defining basically what is the result set we are going to operate on, and you know, I'm just reading out the last 15 minutes of the new data added for a given stock item ID. And then, you know, in this CTE, what I'm doing, I'm just executing this correlated subqueries to calculate the running total and to calculate the percentage of each row on the total, right? And the result, as you can see here below, I just executed the query because it was taking quite some time, is returning around 11,000 rows in 1.47 minutes. Okay, if I'm now executing the same exact query from a functional perspective, leveraging window functions, you can see this is effectively taking around 100 milliseconds. So the difference in time is really, really impressive. And you know, you can see the number of rows are slightly different. This is because, you know, remember, we are filtering out the last 15 minutes, and there are new rows and you know, coming in at any time. So it, you know, the result set is slightly different, but you know, is the same kind of overall size and comparable you know, type of results. But you know, the performance are super impressive. And the reason why, you know, we had such a great performance here is because as we can see here, the estimated execution mode is batch, right? And the kind of window aggregate operators are working in this batch execution mode, and the overall efficiency of this query plan is really impressive compared to the kind of correlated subquery type of approach, right? So again, I think the combination of the window function operators and the batch mode is what is really giving us this level of performance, which is really impressive. And there are a number of window functions available in Azure SQL and SQL Server engines. starting from kind of ranking functions where we can effectively kind of generate a row number for a given result set. We can kind of rank data in various forms and shapes, aggregations, of course, all sorts of aggregations, including statistical deviations and variance, and a number of other kind of very powerful analytical functions that can resonate around that kind of windowing mechanism that window functions are providing. So to recap, in the real world, we know applications are running kind of mixed workloads that are not pure OLTP or pure OLAP, but we need to make sure that our data tier can effectively run this mixed workload in an efficient way. And while in some cases consolidating all the data into a central kind of enterprise type of data warehouse can cover most of the analytical requirements, it introduces this kind of latency and lag between operational data and reporting and dashboarding solution. This is why for kind of real-time operational analytics scenarios, we can run those mixed workloads by leveraging technologies like column store indexes, in-memory OLTP, optimized tables, and natively compiled functions and window functions in order to kind of provide this powerful tool set that application developers and data engineers can use to power HTAP solutions on Azure SQL. You will get all the details from a documentation perspective, all the samples that I've been using here, and some additional information around how to run real-time operational analytics in those links that you will find available in the slide deck that I'm going to share. And last but not least, thank you all for attending the session, and thanks to the Data Platform Geeks folks for organizing this very nice online event. By the way, don't forget to apply for those kind of prizes for this competition. Please post kind of your selfie with this hashtag and provide session and conference feedback, and make sure to follow those Twitter handles to receive all additional information about the event. Thanks again, and have a great day.